I have to be completely honest here, Nathan. Actually, what I've done is I've divided this unit into two chunks. I've broken it up into conservation of energy. That's going to be your test next class. And then conservation of momentum. They used to be assessed the same on the provincial exam. Oh, got a latecomer here, ruining my little intro. So I've broken this unit up into two chunks. That means that probably you're going to see, Petra, a lot of work energy combined questions showing up later too. In fact, the last lesson of this little mini section is going to be, in a few days, questions that involve conservation of momentum and conservation of energy. They're both, the title of this unit is actually conserved quantities. Energy, momentum. So one of the most important concepts in physics is the idea of momentum. Newton first used the concept when he phrased his second law of motion. He actually never wrote the equation F equals ma. He wrote it in terms of impulse and momentum. He called the product of mass and velocity quantity of motion. But this product has come to be known as momentum. Basically, it's the amount of motion an object has. What makes momentum so important is that momentum is a conserved quantity. Now, Kelly, you may be saying, meh, energy is conserved too. The problem is, Kelly, there's so many different types of energy, even though in theory energy is conserved. In reality, we lose a lot along the way, to heat, to sound, and so we're having to fudge our calculations an awful lot. Momentum is nicely conserved, and there's not that many different types, and it's a little easier to identify and to spot. In an isolated system, a system which has no external forces, the total momentum of the objects will remain constant. This is the law of conservation of momentum. Big deal, huge deal. Any moving object has momentum. Momentum, symbol P for product, because M for mass is taken, is calculated by multiplying the mass times its velocity. Momentum is mass times velocity, or it's P equals mv. And you'll notice I added vector bars because it is a vector. What direction? Its direction is in the same as the velocity. That's where it gets its direction from. The units. What do I measure mass in? Kilogram. What do I measure velocity in? The units are kilogram meters per second. They haven't shortened that one, Neve, and given it a name, although they're talking about renaming that an Einstein, because he doesn't have anything named after him, and he probably should. Just the same way as a kilogram meter per second squared was renamed the Newton in Newton's honor. Momentum, I wrote here, is a vector quantity, and the direction of the momentum vector is the same as the direction of velocity vector. And here's what that means when you add momenta, which is the plural momentum. When you add more than one momentum, you must use vector addition. Hey, how do we add two vectors together? Why, we draw them tip to tail, tip to tail. The most common mistake, Sam, kids get so used to conservation of energy, they think conservation momentum, they add the momentum like scalars. You cannot. Newton's second law can be rewritten in terms of momentum. In fact, this is how Sir Isaac Newton gave his second law. F equals ma. F equals m change in velocity over change in time, which was actually the definition of acceleration. And then I wrote in brackets final minus initial. Oh, this is m v final minus v initial over time. And this here is really the change in momentum.
Because if mass times velocity is momentum, mass times change in velocity is change in momentum. This is how Sir Isaac Newton wrote his. He said it's change in momentum over time. That's another way to write MA. Sir Isaac Newton said the force is equal to the change in momentum divided by the time. This formula is sort of on your formula sheet, except on your formula sheet, we got the change in momentum by itself. We moved the t over. How would I move the t over? Multiply it. We'll get there in a second. Newton's second law can be stated in words in terms of momentum as follows. If you have an unbalanced or net force acting on a body, that changes its motion so that the rate of change in momentum is equal to the unbalanced force. You guys stay on this page. Let me go back here. This is saying the rate of change of momentum, so there's your change in momentum. To find the rate of anything, it's divided by time, is equal to the changing force, the unbalanced force. Impulse. If the equation for net force just derived is rearranged by multiplying both sides by t, by change in time, then we have, this is the impulse equation. This is the impulse equation, where impulse is defined as, who remembers what impulse is from last year? You're right. Loudly. When I say you're right and you still whisper, trust me, you're right. Impulse is defined as you know what? Put a star, whatever. This is what drives me crazy. I'm telling you, Josh, on the test, I'm going to say, find the impulse. And what I really mean is find the change in momentum. And how do I find change in anything? What's change in anything? Okay, final minus. You all know that now, but the number of times I'll say, hey, what's the impulse? And kids will leave it blank. Or I'll say an object has an impulse of -3 kilogram meters per second, and kids won't know what to do with it. It's change in momentum. It's change in momentum. Impulse and change in momentum, interchangeable. What's impulse? Change in momentum. What's change in momentum? Another word for impulse. Okay? Here's what that means then. You can get a change in momentum in several ways. You can change the momentum of an object by applying a big force for a short time, say getting hit by a bullet, or a small force for a long time. Slowly pushing that person with 2 hands will also gradually cause them to move. The worst ones are a big force for a big time, say getting hit by a locomotive. Units for momentum and impulse. So, momentum has measuring units which have the dimensions of mass times velocity. Impulse has the dimension units which are force times dyne, which are Newton seconds. However, it turns out that means this. If F delta t equals m delta v, if impulse equals change in momentum, if change in momentum equals impulse. If that's true, that must mean that kilogram meters per second must be the same as Newton seconds. Doesn't it, Claire? Must. Because if those equations are the same, the units must be the same. And the left-hand side definitely gives me a force times newtons times second, and the right-hand side is mass times velocity, kilogram meters per second. Oh, and the right-hand side is impulse because change in momentum, the mass isn't changing, the change in velocity, the velocity is changing. You can also do impulse where the mass is changing. We won't look at that this year, but that actually is often what's going on, say, with the space shuttle, where you're losing mass as the fuel burns. But we're not going to look at that. This brings us to the law of conservation of momentum. If you have an isolated system, the total momentum remains constant. And there's several ways to write that. You can write it as follows. Jordan, do you think I'm ever going to write out the English version again? No. Okay? We're going to use some notation. Does anybody know what that symbol means? Sigma, yes. What does it mean? It's an abbreviation for. So, what, Michael? Or the total. The total momentum initial has to equal the sum of all the momentum final. That's often my starting point. If my starting point for velocity, acceleration, distance was a tendency to defic, to list my data, if my starting point for forces was this is a job for a good what? Free body diagram. My starting point for momentum is the sum of all the momentum before equals the sum of all momentum after. For two objects, that means this. Momentum of object 1 initial combined with momentum of object 2 initial equals momentum of object 1 final, momentum of object 2 final. If I'm lucky, sometimes some of those are zeros because they're at rest, but not necessarily. And you'll notice, Claire, hopefully I'm being way more careful with my vector notation. I am reminding myself every chance I get, don't you dare just add these. We're going to be dulping a lot. We're going to be drawing pictures a lot. We're going to be trigging a lot. Even if they're in a nice straight line, even if there's no angles, we'll have to be careful because, hey, what's 6 plus 5? 11. What's 6 plus 5? 1. I'll have to make very certain I look at direction, 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 direction. Oh, what's 6 plus 5? Trig. Trig. It's cosine law or SOHCAHTOA or sine law or something. This is my starting point, almost always. When do I use momentum? First of all, when do I use conservation of energy? Is there a change in height? Is there a change in speed? Is there a curvy path? Probably a job for conservation of energy. When do I use conservation of momentum? If there's a collision or an explosion. Oh, you know what? If there's a collision or an explosion, the joke I make with my students, I use conservation of momentum if there's a jean. Collision, explosion, start with what I highlighted in yellow, and then we'll break it down from there. Example 4. If conditions are such that the car and the truck end up at rest, turn the page, end up at rest after the collision, how can we say that the momentum has not been lost for the system? So if they both end up at rest, I can tell you the sum of all the final momentum must be 0. Why? Because momentum is mass times velocity and there ain't no velocity. What does that mean? It means that the momentum before the collision had to have been 0. Wait a minute, Dueck, I got stuff moving before the collision. Let's look at before. Before, we have the momentum of the truck initial and the momentum of the car initial. Momentum is what times what? So this is going to be mass of the truck, V truck initial, plus mass of the car, V car initial, except I'm going to put vector signs over my v's to remind myself there is direction, 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 direction. Vector, 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 vector. Hey, what is the mass of the truck? 2,400? Hey, what is the mass of the car? Sorry, what is the velocity of the truck? I'm sorry. What is the velocity of the truck? 10? Plus? What's the mass of the car? What is the velocity of the car? Ah, negative 24. When you go 2,400 times 10 plus 1,000 times negative 24, hey, what do you get? You know what your momentum was before the collision? 0, and that's why your momentum after the collision was 0. It works. Momentum is conserved. It is possible to say that no momentum was lost because there was none to begin with. So the law of conservation momentum can be written in several ways. You can write it as momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. You can, because momentum is mass times velocity, you can go m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. But my starting point almost always, Cliff, is that guy there. The sum of all the initial momentum has to equal the sum of all the final momentum. We use conservation of momentum when there is a collision or an explosion. A rifle bullet of mass 0.060 kilograms leaves the muzzle with a velocity of that. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil when the bullet is fired? Is there a jeune? Is there a collision or an explosion? I would argue firing a rifle, that's an explosion. It's a controlled explosion, but it's an explosion. You know what this is a job for, Callum? Conservation of momentum. I'm going to start out by saying, hey. I'm going to start out by saying, I don't want that color. I'm going to start out by saying, hey, the sum of all the momentum before the pulling the trigger equals the sum of all the momentum after pulling the trigger. Before I pull the trigger, what's the total momentum right now? How do you know? Because momentum is what times what? Mass times velocity. You see any masses with any velocity before I pull the trigger? Usually that won't be the case, but this time that'll be conveniently true. Bang! I pull the trigger. After I pull the trigger, which masses are moving? It seems to me there's going to be the momentum final of the rifle and the momentum final of the bullet. Get used to it, folks. Lots of explosions in this unit. Sorry. Momentum is what times what? So this is going to be 0 equals m rifle v rifle final vector plus m bullet v bullet final vector. Look carefully at this question. Has it talking about any angles? Do you see any norths of souths? Do you see any degrees? Anything like that? This is what we call a linear momentum question. It's still going to be vector math, but we can do this by letting one way be positive and one way be negative. So this approach, Kelly, the 3 lines that I've just written, works whether there's angles or not, because I've been careful. I've been writing vector equations. When you get to plugging in MV, then you have to say, all right, is my next line going to be drawing a picture with angles and stuff? Or can I just let to the right be positive and to the left be negative? Do you see any angles, any weird stuff in then I can just let to the right be positive and to the left be negative. So I'm going to go something like this. What's this question asking me to find? Velocity of the rifle? Yes? How would I get the velocity of the rifle by itself? I think I would minus this to this side and then divide by what? Can't see it, so let's write it. I have negative MB VB final equals mass of the rifle V rifle final. How would I get the V rifle final by itself? Okay, so the final velocity of the rifle is going to be negative in the opposite direction of mass of the bullet, 0.06. It's a fairly heavy bullet. Velocity of the bullet, 600, 6 times 10 to the 2, divided by mass of the rifle, 3. With what velocity will the rifle recoil? Yeah, I got that. How big? Sorry? Negative 12 units. Negative 12 even? Negative 12 units? It's a velocity, meters per second. What's the negative telling me here? If they'd given me a picture and I knew which way the bullet was going, I could give my answer in terms of left or right or north or south or something. You know what? That negative, in the opposite direction of what I'd let be positive, which was the bullet. Backwards! Boom, backwards. Football. Football. How far am I going to get today? Ooh, don't think I'm going to get through all this today, but that's all right. You guys get to study some for your test. Football. What is the momentum of a 112 kilogram football player running at 4.8 meters per second? Okay. What's the symbol for momentum? P. Momentum is what? How do I calculate momentum? Mass times velocity. So it's going to be 112 times 4.8. I think we'll assume the football player is running forward, so we'll consider that positive. What is 112 times 4.8? 112 times 4.8, 538 if I go to 3 sig figs. Units, kilogram, meter per second. B. What impulse? Hey, what's another word for impulse? Curtis? What change in momentum must a tackler impart to the football player in A to stop him? Hey, what's change in anything? This is going to be final momentum minus initial momentum. Now, the fact that it says stop him, I know my final momentum, it's going to be 0, because that's the definition of stopped. What's the initial momentum? Before the tackle, how much momentum does this football player have? 538. I can do this in my head. It's going to be negative 538 kilogram meters per second. What's the negative saying? The change in momentum has to be applied in the opposite direction of the initial velocity, which, if you think about it, makes sense. Josh, you play football? Okay. If you're running towards me, I have to tackle you in the opposite direction that you're running. That's the best, most efficient way to bring you to a stop. Now, I can tackle you from the side, because momentum is a vector, and probably bring you down, but I bet you you'll get a couple of more forward steps still. That's the difference between tackling head on and bringing somebody down from the side. They usually get an extra stride or two because you're having a tougher time canceling out their momentum because you're taking in a vector component. Is that all right? What's C asking me to find, Josh, my friend? Average force. What else did they give me in part C? What is that, 1.2? Yeah, what is that? So, ready? What else did they give me in part C? And one-word answer begins with the letter T. Is there an equation that has change in momentum and force and time in it? Why, yes, there is. In fact, I think this is one of only 2 equations in the momentum section. You guys have this, yes? F delta T equals... Is that on your formula sheet? I can't even remember. Yeah? Okay. Josh, what did this question want me to find? Oh, how would I get... what did this question want me to find? Careful, read carefully. Oh, force. F! How would I get the force by itself here? In this equation? Divide by time. Okay? It's going to be negative 538 divided by 1.2. Callum, I know you also play football. 1.2 seconds for a tackle. Is that way too long, way too short, or just right? It's way too long. First of all, a good hit, pretty quick, maybe a quarter of a second. Certainly, I think most tackles are a half to 3/4 of a second, but I was making up numbers on the fly. But I just wanted for my football players to reassure them, I know this is not realistic. Divided by 1.2, 1.2, negative 448 newtons. Josh, you're my football player? Yes? What if I want to make this smaller? What if I want to stop him quicker? I still got to cancel out his momentum. If I want to stop him quicker, what must change on this equation here? But yeah, but if time goes down, what else has to happen then? I've got to hit him harder. Force has to go up. That's why the biggest hits are the most explosive, quickest hits as well. Okay? Because I'm stuck with the change in momentum. I'm stuck with, in any tackle, the final momentum is always going to be what? Think about it. Just like in any car accident, the final momentum is always going to be what? 0. In any tackle, the final momentum is going to be, because the guy comes to a stop, right? So I'm kind of stuck with this. This is also why, going on a little football rant, the freakiest running backs in the NFL are the fast, really heavy running backs. So Adrian Peterson is a bit bigger than normal. You guys don't remember, back in the late 80s, early 90s, Christian Okoye played for Kansas City. His nickname was the Nigerian Nightmare. He was actually a converted rugby player from Africa who was about 6'4", about 255, and could run like a deer. And so for 2 years, he led the NFL in rushing because he had a lot of momentum. He was big and fast. The only problem is there comes a point when human physiology starts to set in. His knees were shot after 3 years. He did an ACL, and that was the end of it. Brandon Jacobs, also big, bruising, like a big running back with a fair bit of speed, but you'll notice what he played. 4 years, 5 years, and so there's limitations that the bone structure can handle. But boy, if you get those really, really big, really, really fast people, they're tough to bring down. They just generally don't have long careers. Sorry? What about, I'm amazed LeBron has not yet blown a knee or done bone damage, because the two people that amaze me, him and Shaq, because every other center, watch, they have the back problems, they missing stuff. Shaq was remarkably durable for the amount of weight, because he was packing over 3 spins his entire career, and all I can imagine is, I mean, he was muscular, so he could pack it well. His bones had to be far thicker than average, because I would have fully expected him to have health issues. And LeBron is the other one where I kind of go, I've never seen. I think you're approaching the threshold of what a human physiology can handle, and the forces and the torques and the momentum changes that you're putting on it. Was there a part D? No. Example 3. Imagine you're doing a spacewalk outside the space shuttle. Woohoo! So there's no cable between you and the shuttle. You're on your rocket pack, and it suddenly quits on you. Now, in real life, when you go out with that rocket pack, there is redundancy after redundancy after redundancy after redundancy. It's not going to quit on you. They've got like 4 or 5 backup things. But let's suppose, worst case scenario, your small maneuvering rocket pack suddenly quits on you, and you are stranded in space with nothing but a $50,000 camera in your hands. How can you get back to the shuttle? Yeah. Okay, I was going to say, you don't just throw the camera. Throw the camera in what direction? Because right now, you and the camera have a momentum of what? 0. So afterwards, after the explosion, which is what throwing something really is, you also still have the momentum of what? So if the camera gets a momentum to the left, you'll pick up some momentum to the... Now you have a bigger mass, so your velocity will be smaller. But yeah, if I carefully line myself up so that I throw the camera in exactly the opposite direction of the space shuttle, I should have some momentum in the direction of the space shuttle. Is that okay? Example 4. I think I like example 4. I think example 4 is a nice question. I haven't looked at my test yet, but this is twigging with me. It's rocket science, so maybe I just like it because it's rocket. I can't remember, but my little math nerd heart's going pitter-pat here. A rocket expels that much kilograms of gas each second, and the gas leaves the rocket with a speed of that fast. Will the thrust produced by the rocket be sufficient to lift it if the force of gravity on the rocket is that there? Well, hey, a rocket expelling gas, that's an explosion. It's a controlled explosion, but that's an explosion. This is a job for, well, conservation of momentum, but I think here, since I'm seeing speed and I am seeing a time and I see them talking about force, I think where I would start out with is impulse. Force, change in time, equals change in momentum. And in particular, I think what we're talking about here is the thrust force. How big is that thrust force? Curtis, let's get it by itself. How would I get the thrust force by itself? Okay. So the force is going to be the change in momentum divided by time. This is how any rocket works. In any rocket, you have mass going out the back, fuel. You have mass going out the back at a certain speed. Okay. By the way, technically it's a change in, but we're just going to look at one single solitary second, so we're just going to go mass times velocity. How much mass? 1.2 times 10 to the third. What speed? 1, 2, 3, 50,000. 5 times 10 to the fourth. What time? Oh yeah, 1 second. Okay. Uh, 1,200, because that's what 1.2 times 10 to the 3 is, times 50. Dueck, you should be able to do this in your head. Well, here you go. You get 6 times 10 to the 1, 2, 3, 4, 5, 6, 7? 6.0 times 10 to the 7th newtons. Before we turn the page, let's draw a free body diagram on that rocket. What are the forces acting on it? Get the obvious ones. Gravity. What else? I gave that force applied a name. Thrust. Yes? Yes? And slightly bigger than gravity? Looking at the numbers, yeah? Who's winning? Really? Who's winning? Huh? We just did a whole test on this a little while ago. Sorry? Hey, cool, cool, cool. You know what? Let's find the acceleration here. So this is going to be thrust minus gravity equals ma. How would I get the a by itself? A equals thrust minus mg over m, where the thrust is 6 times 10 to the 7th. Take away 5.8 times 10 to the 7th, all divided by... Mr. Dueck, they didn't give me the mass. No, but they gave you the weight. 5.8 times 10 to the 7th, divide that by 9.8, and that should give you the mass. What's our acceleration going to be? Let's try that again. Bracket 6e7 minus 5.8 times 10 to the 7th divided by bracket 5.8 times 10 to the 7th divided by 9.8 to get the mass. You get that? Or am I wrong? 0.338? Curtis is smiling almost sheepishly, saying, hey, that ain't very big. It's not. Ah, but wait, Curtis. As you burn fuel, what happens to the overall mass? What happens to this number here? As you burn fuel, decreases. Does your thrust change? No. So that top number stays the same, but the mass goes down. So this acceleration slowly increases, and that's beyond our skill to handle right now. You need calculus. But eventually, I think that acceleration, assuming you have a fair chunk of fuel, it'll get up there. Turn the page. Read example 5. Is there a collision? This is a job for momentum. Do you see angles or norths of souths or anything like that? So I'm not going to freak about vectors. I'm probably going to let one way be positive, one way be negative. I'll be careful that way. You ready? Harjo, you said there was a collision? This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Can I call the 3.2 cart 1 and the 1.8 kilogram cart 2? And let's decide from now on, we'll just read from left to right, and the first thing that I see, I'll always call cart 1, and the second thing that I see, I'll always call mass or cart 2, and that way our stuff will look the same. So, before the collision, what's moving? Mass 1, mass 2, or both? Hakeem, sorry? Momentum of 1 initial. Wham! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Okay, if they were separate, don't write this down, don't write this down. If they were separate, I would go momentum 1 final and momentum 2 final. But since they're stuck together, I guess I'll go momentum all final. Momentum is what times what? So this is going to be mass 1 V1 initial vector bar, to remind myself to be very, very, very careful here. Wham, they collide. And this is going to be mass 1 stuck plus mass 2 V final. There's the momentum of all of them after the collision, stuck together. What's this question asking me to find? Which velocity? Oh, V final? How would I get the V final by itself? Divide by what? Okay, so if I hear you finally correctly, Elijah, and I think I do, you're saying V final is going to be the first mass, the first velocity initial, divided by that. So it's going to be 3.2 times 1.2 divided by 3.2 plus 1.8. Cliff, what'd you get? Sorry? Sorry, I missed that. 0.768 meters. Positive or negative? They kept going in the same direction as the original cart because I let the original cart be positive. Is that okay? Not a big fan of number 6. So skip number 6. The reason is I have the cart going this way along the railroad tracks, and it says a load of coal is dumped. I think the coal would kind of get dumped like that. I don't know. I'm not a big fan of number 6. I do like number 7. Read number 7. Ashley, is there a collision? You know what this is a job for? Conservation of momentum, you say. The sum of all the momentum before the collision has to equal the sum of all the momentum after the collision. I see two cars before the collision. What's moving? Car 1, car 2, or both? Both? So I'm going to go like this. Momentum of car 1 initial before the collision combined with plus momentum of car 2 initial before the collision. Wham! They collide. Every time, Petra? Every time? After the collision, Petra, my angel, after the collision, what's moving? Car 1, car 2, or both? Stuck together or separate? Oh, so I'm going to go momentum all final. Otherwise, I'd go momentum 1 final and momentum 2 final separate, right? Oh, and if it's not moving, it's 0 and I don't even write it, right? Okay. Petra, look carefully at this question. Do you see any angles, any degrees, any north of south, east of... Okay, so all we'll have to be careful of with here is positives and negatives. No trig, no dolp. By the way, you want to get used to asking yourself that question right around here, because if there are angles, our next strategy is going to be totally different. It's going to be lots and lots of pictures and lots of trig, but no angles. What are we trying to find here, Petra, my angel? You know what? Let's substitute in what momentum is. Momentum is what times what? Mass times velocity. Okay. How many more do I have here? A few more, good. We'll stop with this one. This is going to be M1 V1 initial plus M2 V2 initial, and I guess that's going to equal, Petra, M1 plus M2. That's the definition of sticking together, yes? V final. What did you say we're trying to find, Petra? Which one of those is, which of the V's am I looking for in this equation here? VF, how would I get the VF by itself? So if I hear you correctly, and I think I do, you're saying this. The final velocity is going to be mass 1 V1 initial plus mass 2 V2 initial, all divided by... Is that what you're saying? You'd be right. All right, let's plug and chug. V final is going to be... How big is mass 1, folks? How big is mass 1? Hello. How big is mass 1? Bree. Yeah, 1,200, right? I think that's what I saw your lips say the first time, actually. How big is V1 initial, Bree? Are you saying 33? I can't hear, but yeah, okay, good. Plus. How big is mass 2, folks? 1,800? How big is velocity 2 initial? Why is 22 wrong? And I'm so glad you did that. Can you underline that there, Claire? Why is 22 wrong? Ah, momentum is a vector. Freak out about direction. Be paranoid. The most common mistake in this unit is direction. Negative 22. All over. I think I can add those together in my head. 3,000, yeah? 1,200 and 1,800? By the way, If I get a negative answer, it means the collision looked like this. If I get a positive answer, it means the collision looked like this. Right? The positive one won the collision as opposed, what do you get? Or do you get 0? Oh, if I get 0 exactly, then it means the collision, even though they were at different speeds and different sizes, looked like this. Came to a stop. I haven't tried this one yet. 1200 times 33 plus 1800 times negative 22 divided by 3000. What do you get? Is it 0? Oh! I must have made that one up on purpose. You know what? This would be a terrible head-on collision. Boom! Everything would come to a stop. Not good. Not good. If I knew, by the way, how long the collision lasted for, I could calculate the average force that each car had to endure. And if I then knew the mass of the driver, I could calculate their acceleration and probably make a guess as to whether it was fatal or not. Right? Okay. We'll pause here.